Think about the sheer power we have, not just to observe the world, but to actually predict how it'll behave.
Yeah, like, will a plane wing bend or break?
Right. Or forecasting weather, or even, how diseases might spread.
And at the heart of all that predictive capability, it's this fascinating realm, mathematical models and numerical simulation.
Exactly. What might sound like, I don't know, dusty old equations are actually incredibly vibrant tools. They help us grasp how reality fundamentally works.
Absolutely. And in this deep dive, we're jumping right in. We're looking at some really fascinating material, exploring these exact ideas,
Uh-huh.
focusing specifically on numerical analysis and optimization.
So we're looking at the blueprints, basically, these predictive tools.
Yeah, often PDEs, partial differential equations,
Yeah.
and also the ingenious methods we've cooked up to actually, solve them and get real answers.
Okay, so our mission today is kind of to demystify this powerful world.
Mm-hmm.
We want to pull out the core concepts of mathematical modeling, numerical simulation,
Yeah.
make them understandable.
Right. And maybe reveal some surprising insights into how these methods actually work their magic.
And why they're just indispensable now.
Yeah, across so many fields. To get you hooked, we'll be touching on a fantastic range of topics from the source material.
What?
We'll explore different kinds of mathematical models, think about the equations for heat flow.
How heat moves through something.
Exactly. Or how sound waves travel, how pollutants spread in water, maybe, or even how solid objects deform when you push on them.
And then we look at how we solve these.
Right. The clever numerical methods, things like the finite difference method and the finite element method.
Okay, and here's where I think it's really interesting. We'll look at these crucial ideas of stability and convergence,
Oh, yeah, absolutely critical.
including that rather intriguing CFL condition.
Mm.
And we'll peek at some of the deeper theory behind it all, like variational formulations and these Sobolev spaces.
That's right. But hold on, there's actually more.
More.
Indeed. We'll also venture into the world of optimization. How do we find the absolute best possible solutions out there?
So not just a solution, but the best one.
Exactly. Could be finding minimum energy in physics or tackling, mind-bendingly complex problems like resource allocation.
Or that classic puzzle.
The traveling salesman problem, yeah.
Yeah.
And finally, we'll see how these seemingly separate worlds, smooth, continuous math, and discrete calculations, they actually come together beautifully.
Okay. Sounds like quite a journey. So get ready, everyone.
It should be enlightening.
Right. Let's start by unpacking this core idea then. Mathematical modeling.
Okay.
Essentially, it's taking messy, complicated reality and creating these simplified, abstract representations, usually equations.
Like blueprints, as you said.
Yeah, blueprints of the real world.
Uh,
Allows us to analyze and, crucially, to calculate and predict.
That's a great way to put it. And a lot of the source material looks at phenomena described by these PDEs, partial differential equations.
Right.
Think about heat flow, often described by Fourier's law, right? How heat moves from hot to cold.
Standard stuff.
Well, yes, but the sources also point out these models aren't, perfect. They have limits.
Huh?
For instance, at really extreme temperatures or super fast changes, Fourier's law can kind of break down.
Break down how.
It leads to this rather strange prediction: infinite heat propagation speed.
Infinite speed. That can't be right. Sounds like sci-fi.
Exactly. It highlights that building a model involves assumptions, right? And you need to know when they hold up.
Okay.
Another fascinating example is the convection diffusion equation.
Convection diffusion. Okay.
It describes how something, maybe heat or a pollutant, gets transported, both by the bulk movement of a fluid that's convection, like wind carrying smoke, and by random molecular motion that is diffusion, like ink spreading in water.
Right. Okay. I see.
And the balance between these two, it's captured by this dimensionless number, the Peclet number.
Peclet.
Yeah. If it's really small, diffusion dominates. Maybe a simpler model, like the basic heat equation, is good enough.
Oh, yeah.
But if it's around 1 or really large, you probably need the full convection diffusion equation. Or maybe even just the advection equation if bulk movement is the main thing.
So it's about choosing the right level of detail.
Exactly. It's like choosing the right map. Simple map for your neighborhood, but you need a much more detailed one for navigating a big city.
Makes sense. What other kinds of real-world things can we model with these PDEs?
Oh, the sources give several good examples. There's the advection equation itself, fundamental for transport phenomena like exhaust fumes from a car.
Okay.
Then there's Schrödinger's equation, absolutely central to quantum mechanics. Describes energy conservation beautifully at the atomic level.
Wow.
And for understanding how solid things like bridges or buildings respond to forces, we have the equations of linear elasticity.
Last it.
Yeah, involves parameters like Lemay constants describing stiffness and boundary conditions, specifying how the object is supported or where forces hit it.
These models sound incredibly powerful, but they're still just equations on paper, aren't they?
Well, yeah.
So this is where numerical simulation comes in, taking these abstract models and using computers to actually calculate solutions.
Precisely. Bringing the equations to life, essentially.
How do we do that?
Well, one of the foundational techniques is the finite difference method.
Finite difference,
So the core idea is you approximate the smooth, continuous changes from the derivatives in the PDEs with small, discrete differences, calculated at specific points in space and time, like on a grid.
So for the heat equation,
You'd approximate how temperature changes over a tiny time step and how it varies over a small distance, just using temperature values at nearby grid points. Simple idea, really.
the source mentions different schemes within this method, explicit and implicit. What's the difference there?
Right. So with an explicit scheme, you can directly calculate the solution at the next time step using only the values you already know from the current time.
Sounds straightforward.
It is, conceptually.
Right.
But it can run into trouble with stability. Small errors might just grow uncontrollably.
Not good.
No. Implicit schemes, on the other hand, they involve solving a system of equations to find the values at the next time step.
So more work per step.
Generally, yeah. More computational effort, but the big advantage is they are usually much more stable.
And stability is absolutely crucial.
Right.
Because if your scheme is unstable...
Your results are garbage.
Yeah.
Tiny errors, maybe from initial data or just calculation rounding, they can amplify wildly. You get nonsensical results, totally unrelated to reality.
Right. Okay, makes sense.
And a key concept tied to stability, especially for time-dependent problems, is the CFL condition.
CFL, current Friedrichs-Lewy.
That's the one. It essentially says that in your simulation, information can't travel faster numerically than it does physically in the real system.
So it links time steps and space steps.
Exactly. For instance, in an explicit scheme for advection, that transport equation, your time step size and your spatial grid size have to be linked. So the numerical speed doesn't outpace the actual physical speed of whatever you're simulating.
Now, the source points out something paradoxical about the advection equation in CFL.
Oh, yeah, that's interesting.
It says, as the diffusion part represented by nu gets smaller and smaller.
Right, approaching zero.
The CFL condition seems like it should be automatically satisfied, but the scheme can still become unstable. That feels wrong.
It is quite counterintuitive. It really highlights the subtle, sometimes unexpected ways different parts of an equation interact when we approximate them numerically.
So even if the main CFL part looks okay.
Right, the condition based just on the advection speed might be met, but the way we approximate other terms, even tiny ones like diffusion, can still introduce instabilities.
Wow, it's a reminder that these are approximations.
Exactly. We need to be really careful about their limitations. The source also briefly brings up the finite element method.
Right, another numerical technique.
Yeah, very powerful, especially good for problems defined by boundary conditions on, say, complex shapes like stress in a machine part.
And it's connected to variational formulations.
That's one of its great strengths, yeah, this connection.
A variational formulation. That sounds like a totally different way to look at these PDE problems.
It is, in a way.
Instead of point-by-point changes, it's more overall, a brighter perspective.
Precisely. The traditional classical way focuses on derivatives at every single point inside the domain. The variational approach reframes the problem using integrals over the entire domain. It looks for a solution within a specific function space, often a Sobolev space.
Sobolev space again.
Yeah, by requiring it to satisfy an integral equation involving a set of test functions.
Okay, integrals over the whole space. The source uses the Laplacian with Dirichlet boundary conditions as an example.
Right, a classic elliptic PDE. Dirichlet means the solution's value is fixed on the boundary on the edges.
And it distinguishes that from Cauchy problems. Can you clarify that difference?
Yeah, sure. A boundary value problem, like that Laplacian example, specifies conditions on the boundary of a region, and those conditions determine the solution inside the region.
Like puzzle edges defining the inside picture.
An analogy, yeah. A Cauchy problem is more typical for time-dependent equations. You specify the initial state at time 0, and then use the equation to see how that state evolves forward in time, like starting a movie and watching it play out.
Got it. And these Sobolev's cases, the source mentions weak differentiation and functions having traces on the boundary.
Right.
It sounds like these bases are just a better fit, more flexible for these variational methods, especially if solutions aren't perfectly smooth.
That's an excellent way to think about it. Sobolev spaces let us work with functions that might have sharp corners or breaks places where classical derivatives might not even exist.
But they still have derivatives in some sense.
Yes. Weak derivatives, defined in an integral sense. And the trace idea lets us talk meaningfully about the values of these potentially rough functions right on the boundary, even if they aren't continuous in the usual way.
Okay.
For example, the source points out that any function in H101 that's a function's on the interval 0, 1, whose first weak derivative is reasonably behaved, is actually guaranteed to be continuous on that interval, including at the endpoints 0 and 1. Which is quite neat.
Okay, that is neat. Now, what's the connection between this variational approach and minimizing energy? The source brings that up too.
This is a truly elegant and powerful connection. For many elliptic PDEs, finding the solution to the variational formulation is mathematically the same.
Equivalent.
Equivalent, yes, to finding the function that minimizes a specific energy functional associated with that problem.
Like physical systems settling into low energy states.
Exactly like that. For the Laplacian with fixed boundary values, the solution actually minimizes something called the Dirichlet energy. It's related to the total roughness or variation of the function.
So it gives us a completely different way to think about solving these. Find the state of minimum energy.
Precisely. It's often very powerful. However, the source rightly notes, this energy minimization view relies heavily on a property called symmetry of the bilinear form in the variational formulation. If that's not symmetric, the direct link to minimizing a simple energy functional might break down.
Okay, that's really insightful. Now, the sources seem to shift gear a bit towards optimization.
Finding the best solution.
Yeah, it feels like we're moving from just describing and predicting to actively trying to improve or control things.
That's a perfect way to put it. Optimization is all about finding the very best choice from a set of available options.
How?
Often by minimizing something we want less of, like cost or energy or waste, or maximizing something we want more of, like profit or efficiency or maybe strength.
The source gives some really diverse examples. Minimizing mechanical energy.
Yeah, like for an elastic membrane or structure, finding its stable shape.
Optimal control, like guiding a robot arm.
Exactly. Steering a system to a desired state efficiently and deciding how to best allocate limited resources. That's huge.
Okay, so how do we actually find these optimal solutions?
Yeah.
The source mentions necessary and sufficient optimality conditions.
Right. Things like Euler's inequality and Lagrange multipliers.
Sounds like the mathematical rules of the game.
They are, essentially. Necessary conditions are things any optimal solution must satisfy. Sufficient conditions guarantee that if a solution meets them, it is optimal.
Okay.
Euler's inequality is useful when the set of possible solutions is convex, a sort of nice, rounded shape without dents. Lagrange multipliers are incredibly powerful for handling constraints, limitations, or requirements that our solution must meet.
Constraints like limited budget or material strength.
Exactly. The source also briefly mentions duality and optimization.
Duality.
Yeah, where you look at a related dual problem. Sometimes it's easier to solve, or it gives you useful bounds on the solution to your original primal problem. And, of course, in practice, how do we find these solutions? We usually rely on numerical optimization algorithms. Things like gradient descent methods are very common for actually finding the minimum or maximum on a computer.
Gradient descent, like rolling downhill to find the bottom.
Kinda, yeah. Following the steepest downward slope of the objective function.
Okay, this naturally leads us into operations research, OR.
Right.
It sounds like OR is where these optimization techniques really get put to work on practical, real-world stuff.
Absolutely. OR is a whole discipline using mathematical modeling, optimization, statistics to tackle complex decision-making problems. Oh, everywhere. Transportation, supply chains, finance, healthcare, manufacturing, scheduling, you name it.
And linear programming is highlighted as a key OR technique. What's that good for?
Linear programming, or LP, is incredibly versatile. It's for problems where your objective, the thing you want to maximize or minimize and all your constraints, can be expressed as linear equations or inequalities.
Okay.
Think about figuring out the best production plan for a factory to maximize profit, given limits on raw materials, machine time, labor hours.
Okay, classic business problem.
Or minimizing the cost of shipping goods from warehouses to stores while making sure every store gets what it needs.
Right. And how do you solve these LPs?
The simplex algorithm is the classic method, widely used. It cleverly moves from corner to corner of the feasible region, the space of all possible solutions that satisfy the constraints, always improving the objective function until it finds the best corner.
The source mentions basic solutions and reduced costs.
Yeah, those are sort of technical concepts fundamental to how simplex works, related to identifying those corners and figuring out which way to move next.
Okay. And then there's integer programming, where solutions have to be whole numbers.
Yes.
That sounds like it makes things way harder.
It certainly does, generally speaking.
Yeah.
Requiring integer solutions, like you can't build half a car or schedule 2.7 workers,
Right.
usually makes optimization problems much tougher to solve computationally. NP hard, often.
But the source points out something interesting.
Yes, a fascinating and very useful result. In some special cases, particularly involving problems that can be represented with what are called totally unimodular matrices,
Okay.
which often pop up in network flow problems. The solution you get by ignoring the integer constraint, temporarily solving the continuous relaxation, automatically turns out to have integer values anyway.
Wow. So you get the integer solution for free sometimes.
Exactly. It's a huge simplification when it happens, a really nice property.
And network flow problems themselves are a classic OR application.
Absolutely. Think about moving stuff through a network.
Stuff like?
Goods in a logistics network, data packets on the internet, oil and pipelines, cars on roads.
Okay.
Network flowing problems involve finding the most efficient way to move this stuff from sources to destinations, respecting capacity limits on the connections, the arcs, and often minimizing cost.
And Kirchhoff's law is mentioned.
Yeah, in this context, it's basically the conservation rule. What flows into any point in the network that isn't a start or end point must also flow out. Flow in equals flow out.
Makes sense. Dynamic programming also gets a mention.
Yes, DP, another very clever technique.
What kind of problems is it good for?
It's great for problems that have two key properties. One is optimal substructure, meaning an optimal solution to the big problem can be built up from optimal solutions to smaller overlapping subproblems.
Okay, and the second property?
Is those overlapping subproblems. You end up needing to solve the same smaller problems over and over again. DP cleverly stores the results of these subproblems so you only compute them once.
Like finding the shortest path somewhere.
That's a classic example, yeah. The source mentions Bellman's optimality principle.
The core idea of DP.
Pretty much. It says that if you have an optimal path from A to C that goes through B, then the B to C part of that path must also be the optimal path from B to C. Seems obvious, but it's the foundation.
Right. And finally, this source briefly touches on greedy algorithms and branch and bound.
Yeah, for tackling even more complex problems, combinatorial optimization.
Like the traveling salesman problem, finding the shortest route through a set of cities.
That notorious one, yes. Incredibly computationally demanding as the number of cities grows.
So how do these methods help?
Well, greedy algorithms offer a simpler approach. Just make the best-looking local choice at each step. Go to the nearest unvisited city, for instance.
Does that work?
It's fast, often intuitive, but it doesn't guarantee finding the absolute best overall tour. You might get stuck in a suboptimal route.
And branch and bound.
That's more systematic, more rigorous. It explores the huge tree of possible solutions, but it prunes branches by using clever estimates or bounds. If it can prove a whole section of the tree can't possibly contain a solution better than the best one found so far, it just skips exploring it.
Still sounds computationally heavy, but smarter than trying everything.
Exactly. It's a way to tackle these really hard problems more effectively than brute force.
Wow, okay. We have covered an enormous amount of ground here.
We certainly have.
From the abstract beauty of mathematical models to the really practical applications of optimizing real-world systems. What are some of the core interconnected ideas we should really take away from this deep dive?
I think the central themes are definitely these powerful, essential connections between the areas. Mathematical modeling, numerical simulation, Variational methods, optimization.
They aren't separate islands.
Not at all. They're deeply intertwined. They build on each other. You use models to describe the world precisely.
Oh, right.
Simulations to get actual usable answers from those models.
Mm-hmm.
Variational methods can offer a different, often more robust way to analyze the problems.
And optimization.
Lets us use those models to find the best possible outcomes, the best decisions.
And it's genuinely fascinating seeing those aha moments,
Mm-hmm.
where seemingly different areas just click together.
Like what?
Like realizing that deep link between variational formulations and minimizing energy in physics. That's pretty cool.
It is elegant. Yeah.
Or understanding how something seemingly theoretical, like numerical stability,
Mm-hmm.
has incredibly direct, tangible consequences for whether our computer simulations are reliable or just, well, garbage.
Exactly. It's not just theory for theory's sake. It has real impact. And I think this deep dive really lays a foundation,
Yeah, for exploring further.
Yeah. If any of these areas, maybe the nitty-gritty of finite elements, or the complexities of optimization algorithms, or the huge range of applications in OR, if any of that sparks some curiosity, there's a whole universe of fascinating stuff out there waiting.
Okay. So as we bring this deep dive toward a close, let's leave our listeners with a final thought, something to ponder.
Okay.
Consider the ever-increasing power of computers and the growing sophistication of all these mathematical tools we've discussed.
Right. Things are advancing fast.
How will this continue to shape our ability to understand, predict, and crucially, optimize the world around us?
What new possibilities does it open up?
Yeah, and maybe what new challenges might it bring? Think about a specific problem or system maybe in your own life or work. Could the concepts we've explored today offer a new lens, a new way to understand it, or maybe even a new approach to making it better?
It's worth thinking about. The journey of discovery in these fields is definitely ongoing.
And it promises to be full of more surprises and insights, I'm sure.